When you have a map and different parts of the map take different times to cross, how can we find the fastest paths? In this map, the dark green represents mountains and they're very slow to cross, so this algorithm prefers to make a detour to go through the mountain pass. The algorithm shown here is called Dijkstra's algorithm, invented in 1959 by Edgar Dijkstra, a pioneer of computer science. He had a great way of expressing himself. One of his famous sayings is, "The question of whether machines can think is about as relevant as the question of whether submarines can swim." The other thing Dijkstra was famous for was his belief that mathematical proofs and algorithmic design go hand in hand, and so from this point onwards in the course we're going to be strict about all the algorithms we discuss, and we'll make sure we write proper proofs that our algorithms are correct. Anyway, back to Dijkstra's algorithm. Let's set out the problem carefully. Dijkstra emphasized that we always need to have a proper formal problem statement, because otherwise all we can do is waffle. So before we can even do that, we better start with a few definitions. Pause the video and read these definitions to yourself. Just a piece of advice, it's so easy to skim over definitions like this and not pay close attention, and if you do that, then it will get very tricky to follow the proofs. The best way to take in this sort of material is to have a pad of paper with you and to copy out any definitions you see. There's something about muscle memory which really does work. So pause the video, get some pen and paper and copy out these definitions. Okay, so now we can write out a proper problem statement. Given a directed graph with edge costs, and assuming that the cost on each edge is above or equal to 0, and given a start vertex S, compute the distance from S to every other vertex. Several points to make here. First, this problem statement asks for us to compute the distance. As we saw in the last video about breadth-first search, once we have an algorithm for computing distances, it's very easy to adapt it to find the paths with shortest distance, and that's just left as an exercise. Next, this problem statement refers to directed graphs. If you have an undirected graph, you could either adapt the definitions in the algorithm in the obvious way, or you could turn your graph into a directed graph by replacing each of your undirected edges with two directed edges. We might as well do all the work for the more general case of a directed graph, but there's nothing much in the difference. Next, there's this condition here saying that costs have to be above or equal to 0. This condition is crucial for the algorithm and the proof. As we go through this video, I want you to stop and think at each stage, does this step work if costs are negative? See if you can spot where in this video we are using the assumption, and then at the end of the next video we'll review and see where this condition bites. Lastly, these corner cases about how we're going to define distance. It's just as well to have a fully specified problem, and if we are going to define them, it's hard to think of any other definitions we could make that would make more sense. I won't say more about these choices, but it's a good idea to look through the proof in the next video and ask yourself why these choices make a lot of sense. Okay, now that we have a proper problem statement, we can go on to think about algorithm design. Here's how Dijkstra's algorithm works. This is what the algorithm's data structures look like at an arbitrary point in execution. We're going to be exploring the vertices one by one, and if we pause the execution and take a look at the state, there are some vertices that we know about and we've already explored, some vertices in the frontier that we've seen but haven't yet explored, and then all the other vertices that our algorithm has not yet come across. The other thing we're going to do is we're going to store a distance at each vertex. This will be the distance from the start vertex S along the best path we've found so far. It's not the true mathematical distance, it's just the best we have computed up to this point in time of the program's execution. Now, at each iteration, this is what we'll do. We'll look at all the frontier vertices and pick out the one with the smallest distance, in this case V. And then we'll explore V in detail and look at its neighbours. In this case, it has two neighbours, W and X. W we've seen before, X is new. and we'll consider the edge costs for these neighbours and decide if this gives us any better paths than what we know about so far. In this case, it gives useful information on both fronts. Let's look at W first. Previously, the best path we had found from S to W had total cost 23, but now we know we can reach it in 16 by using the path via V and then taking this new edge from V to W. As for X, we had never seen it before, so we can set best distance found so far to be 17, i.e. distance to V plus the edge cost from V to X. So, we've got a new set of frontier vertices, X and W, and we'll mark V as already explored. And the algorithm just goes on like this, greedily picking the closest frontier vertex at every iteration. Good, so let's turn this into code. Pause the video, read through the code, and see if you can figure out what each bit does. Let me just point out some highlights. Here, line 5, where we declare to explore to be a priority queue. This will be our collection of frontier vertices, and we'll start it off with a single element S. Don't worry just yet about what the priority queue is or what this syntax about sort key and lambda v means. We're going to get to that in a moment. Next, the main loop. We're going to repeatedly pick out the nearest frontier vertex. In other words, the frontier vertex with the smallest distance value. That's what this popmin on line 9 does. Ignore the comments on lines 9 and 10 for now. These are placeholders that we're going to be using in our proof of correctness. Next, lines 11 to 13, where we scan through all of V's neighbours. We're only interested in those neighbours where the path via V is an improvement on what we knew before, and that's what line 13 is testing for. It's looking for neighbours where v.distance plus the cost of the edge is better than the distance value that we had stored for W. Some neighbours like X are entirely new, so we add them to the priority queue. That's what the push on line 18 says. And some neighbours like W we knew about already, but we want to update their distance, and that's what the decrease key on line 16 does. Okay, so that's the basic iteration loop. Now, let's look a bit more closely at this priority queue business. First, a reminder of what we want it for. We need our data structure to support 3 operations: popmin, decrease key, and push. Popmin pulls out the vertex with the smallest distance, decrease key alters the key for a vertex we have stored already, and push adds a new vertex. Now, in the normal definition of a priority queue data structure that you've seen already in the course, we say it stores pairs consisting of 2 parts, a value and a key. But the way I've written this code is just slightly different. Here, the value is a vertex object, and the key is the distance attribute of that object. So I'm basically combining the value and the key into one object. This means I need to tell the priority queue how to get at the key for a given vertex object. And that's exactly what this sort key statement on line 5 does. It's up to you how you write out the algorithm. You could write it all out with key value pairs, or you could write it out with combined objects like I've done here. I just think it's a bit more Pythonic to do it with a combined object. It fits in with how Python lets you do sorting of a list on an arbitrary key, so that's why I've written it out this way. But we still do need the decrease key operation on line 16. That is where we tell the priority queue, hey, I've changed the key that's stored inside W, so please go away and check it out and do whatever you need to do with the new key. Okay, so that's a description of the algorithm. But before we go ahead, I want you to stop and run through this algorithm step by step, pen and paper, on a concrete example. Here's an example for you to work on. Find the shortest path from vertex 0 to vertex 6. From now on, I want you to do this sort of exercise for every single algorithm we encounter. Draw out a small example and just run through the steps hand by hand. That's far and away the best way to get to grips with an algorithm, far better than just passively watching a video. This particular graph is taken from the book Algorithms by Sedgwick and Wayne, which is my favourite textbook for all this stuff. So if you want to check up all your working, look it up there. Okay, so pause the video, work out this example. This is the answer you should have come to. Total distance from 0 to 6 is 151 along this path here. Okay, that's the algorithm. Now let's analyse its performance. First, lines 2 and 3, which loop over all the vertices, is just big O of v, of course. Then some big O of 1 operations. Now, this is where it gets interesting. The main iteration loop runs over and over again, popping a vertex each time. And here is a big claim. This happens at most v times, since a vertex can be popped at most once. That's not at all obvious just from looking at this code, but it's true, and it's something we're going to prove in a moment. And it's important enough that I want to codify the fact by writing it down as an assert statement here in the code. This assert says v is never put back into toExplore. It's certainly not something we can check while the program is running, because it's a statement about what's going to happen in the future, or rather not going to happen in the future. So an assert statement like this is not meant to be a line of code, it's meant to be a placeholder for something we're going to prove in a piece of mathematical analysis. Assuming this assertion is true, then once we pop a vertex, we never push it back into toExplore. Therefore, each vertex will be popped at most once. Therefore, the main iteration loop happens at most big O of v times. Next, the loop over a vertex's neighbours. For every vertex we pop, we loop over all its outgoing edges, and we never pop a vertex more than once, so we never look at an edge more than once. So these lines 12 to 18 are run at most once per edge, in other words big O of e times during the course of the entire algorithm. And adding these all together, this is what total we get. Big O of v plus big O of v times the cost of pop min plus big O of v times the cost of push or decrease key, whichever is worse. So you must be asking, what's the cost of these operations on the priority queue? Well, the technically correct answer is it depends on how you implement the priority queue, and technically correct is always the best sort of correct. But there's one particular implementation of priority queue that's worth knowing about, a very sophisticated data structure called the Fibonacci heap, which is in fact invented for the purpose of making Dijkstra's algorithm run fast. We'll study it in detail later on in this course, but for now all you need to know is that the cost of these operations is big O of log n for pop min, big O of 1 for push and decrease key, where here n is the number of items stored in the priority queue. So for Dijkstra's algorithm, how big can n be? Well, we said that a vertex can never be re-pushed back into the priority queue after it's been popped. That's what the assertion on line 10 said. So n is at most equal to v, the total number of vertices. Okay, putting it all together, the total cost is big O of e plus v log v. So that's Dijkstra's algorithm. Well, or maybe not. Here are Dijkstra's own words. The programmer's task is not just to write down a program, but to give a formal proof that the proposed program meets the equally formal functional specification. In Dijkstra's view, we've barely begun to study Dijkstra's algorithm. All we've done is throw down some pseudocode and waved our hands around. So far we've just been script kiddies, we haven't actually bitten into the real meat of algorithm design. And that's what we're going to do in the next video. By the way, that question I posed at the beginning about what goes wrong if some of the costs are negative, I don't know if you can spot the problem just by looking at the code. Maybe you need to invent a few examples with negative costs and work through them by hand to see what will go wrong. I like to look for problems in a different way. I like to see if I can persuade myself that the algorithm has to work. And if I can't manage to persuade myself that it has to work, then my guess is it doesn't work, and the place where I couldn't persuade myself is a hint about where the problem lies. In the proof that we're going to work through in the next video, there are some steps in the proof that just don't work when the graph has negative costs, and flipping it around, those steps will hint to us where the algorithm concretely goes wrong.